Thank you. Thank you, everyone, for sticking around. It's been a long week, but a good week. So it's always good to be back in Santa Cruz. This year, what I want to talk about is some work that I've been doing with the full sample of Milky Way mass galaxies that we've simulated with the Fire 2 physics as part of the Fire project. This is work that I've been doing with Phil Hopkins and Andrew Wetzel, Robin Sanderson, Kareem El-Baldry, and Zach Hafen, and the entire Fire collaboration, of course. So, come on. Looks like that's not working. Okay, so just a little words about our sample. The Fire 2 Milky Way mass sample now includes about 15, or exactly 15 galaxies simulated with MFM hydro and the improved Fire 2 models for star formation and feedback that we heard some about from Coral and Dushan earlier this week. Of those 15 galaxies, 8 of them are in local group-like pairs, so 4 local groups. The remaining 7 are isolated Milky Way mass galaxies. 3 of those 7 are from the Latte suite that Andrew Wetzel published one of those earlier, or late last year, I believe. So our baryonic particle masses range from 7,000 in those high-res Latte simulations to 55,000 solar masses. Important for this study, our stellar softening lengths are less than or about 20 parsecs in all cases, so we're confident that we're resolving the scale of the disk. And our halo masses range that I'm going to use from about 0.85 to about 2 by 10 to the 12, with stellar masses that go from about 0.4 to 1.5 by 10 to the 11. And again, just to highlight, I'll tell you what our star is exactly in a minute, but to highlight the range of morphologies that we have stellar radii ranging from about 2.5 to 17.5 kiloparsecs in this relatively small mass bin. So before we get to looking at what drives morphology, we have to first quantify morphology. So we looked at how to do this in a lot of ways, and the way that I ultimately settled on was through kinematics. So we're going to do it with what I like to call the JZ plot. So we've heard a little bit about JZ over JCirc. Thank you. Earlier this week. So JZ over JCirc relates the component of the angular momentum that a given particle has that's aligned with the disk to what it would have if it were on a circular orbit. So let me go ahead and show you one of the examples. This is M12F, one of the Latte simulations, not yet published though. Let me break this plot down for you. For the first, let's focus on the purple line. The purple line is the gas in M12F. And that all piles up at 1, which corresponds to perfectly co-rotating, right? This is a distribution of mass. The colored line, meanwhile, represents the stars, and I've gone ahead and colored it by the average age of the universe when stars in that bin formed. So you can see the co-rotating stars are all young, while the dispersion-dominated bulge is relatively old, and then we have a tiny bit of anti-rotating stars that are also quite old. Now what I'm going to do is just define a disk fraction that I'm going to choose to be the fraction of stellar mass in the galaxy with JZ over JCirc greater than 0.5. So that's this dashed line here. For this galaxy, that gives us a disk fraction of 0.6. Now, our sample ranges from disk fractions about 0.2 to 0.8. So here I'm showing just a few representative galaxies. So on the left, we have Batman. Batman is entirely bulge dominated and actually has a small counter-rotating young disk, which I'll tell you about in a minute. Then we have Remus, which has a clear bulge and a clear disk. We'll get to that too. And then finally, we have Romeo, which is just entirely disk dominated and has almost no bulge whatsoever. Just to show you the full sample very quickly, I don't want to talk about this for too long, but I do want to highlight that this result that the bulge is older than the disks and disks form at late times is borne out in our simulations. Now we wanted to have a spatial measure as well, partially to compare with previous work and partially to compare with our kinematic measure. So what I'm going to use is R star, which I'm going to define as the two-dimensional radius that contains 90% of the stellar mass. So this is basically the full radial extent of the galaxy. So again, here I'm showing Batman, Remus, and Romeo. You can see that Batman is very tight, very condensed, whereas Remus and then Romeo are correspondingly more extended and more radially flattened, as you can see in the lower panels, which plot edge-on visualizations. Again, full sample. These are ordered in increasing disk fractions going across and then down and across and down. You can see that the same trends generally hold. As you increase in F-disk, you go from these tight, bulge-dominated systems to large, extended disks. To make that a little more quantitative, here I'm just plotting F-disk on the x-axis and the radial extent on the y-axis. You can see that they are definitely correlated, but there's a fair amount of scatter about them, which helps motivate looking at both of these properties, I believe. Now, before I move on to looking at halo properties or galaxy properties, I want to quickly compare the other morphological measures that we could come up with. So, for example, the stellar flatness of the disk. This is 1 minus z over r, basically. The stellar spin parameter of all the stars within our VIR. The axis ratio of stars within, for example, here it's 20 kiloparsecs. It doesn't really matter what you choose. Broadly speaking, all of the morphological parameters correlate pretty strongly with one another. Now, one more morphological parameter I wanted to look at, because this has gotten a lot of discussion in this meeting, is the sigma 1 parameter, right? So this is the surface density of stars in the central kiloparsec. Now, people asked me, what does this look like for your simulations? And so I went ahead and made the plot, and then I was surprised at how tight the correlation was. So the different colors here just plot different orthogonal views of the galaxy, but there's a very strong anti-correlation between morphology on the x-axis and sigma 1 on the y-axis. Now, if you think about this, this is actually not too surprising because we're looking at relatively fixed mass, right? So if you pack more stars into the central kiloparsec, so you bump up sigma 1, you're necessarily going to have a smaller radial extent, which we saw correlates very strongly with a lower disk fraction. Now, I know that sigma 1 is usually talked about at high redshift, or redshift 1 or 2, but nonetheless, I thought it would be informative to go ahead and show what this looks like at redshift 0. Okay, so now we can start looking for correlations between morphology in our sample and various properties of the galaxy or the dark matter halo. And the first thing that we wanted to do was test the Momau-White model. So this is a famous paper from '98. They basically assumed that if baryons are initially distributed like the dark matter, and baryons acquire their angular momentum from their halos, then you get a correlation between the extent of the galaxy, the size of the galaxy, and the spin parameter and the virial radius. So it basically scales as lambda times r vir with c to the -3 or so, concentration to the -3. So here are our galaxies. I've gone ahead and colored these by the halo mass, just to illustrate that none of these trends, except for, of course, r vir, are driven by the halo mass in this small mass bin again. And the green lines plot the predictive scalings with the Momau-White model with just arbitrary normalizations, best fit normalizations in each panel. It might be a little hard for you to see them, but I've also gone ahead and done just a best fit power law in the gray lines on here. If you can see in the concentration and the virial radius, we actually get inverted scalings relative to what Momau-White predict. Now again, this is over a relatively small mass range, but only the spin parameter correlation seems to be borne out by our simulations, and that's with a lot of scatter about it. So then we said, well, why don't we look at the morphology as shown by the disk fraction, it's a function of spin parameter, and there's even more scatter in this relationship. So I guess I just don't have a ton of confidence in this. To drive that home, here I'm circling two galaxies that have nearly identical spin parameters. One of them is our third smallest and third most bulge-dominated galaxy. The other one is our largest and most disk-dominated galaxy. Right? So there's a ton of scatter about this relationship, if there is indeed a relationship. So then we wanted to move on and say, okay, well, this is unsatisfying to us. Are there other potentially non-halo properties that correlate with the morphology of the galaxy? And so I built this enormous parameter space and searched for correlations between as many properties of galaxies and halos as I could think of, although I'm certainly open to suggestions from other people. The thing that eventually popped out at us was the evolutionary growth histories of the galaxies, which is probably not surprising when people think about it. So here I'm plotting Batman, M12I, this is Latte actually, and Romeo. So again, this is a bulge, somewhat bulge plus disk, and then purely disk-dominated galaxy. And I want to highlight a couple things here. First of all, the blue and magenta lines, which you can barely even see the magenta line typically because it's covered up by the blue line, those plot the gas in the halo and the halo mass. So the total gas within our viewer tends to grow basically in lockstep with the halo mass itself. Now the white line plots the stellar mass of the galaxies, but the yellow line here is plotting the amount of gas in the galaxy itself. So this is basically the star-forming reservoir of the of the galaxy. So what we can see if we look at Batman, we have this huge spike early on, whereas M12I has a spike around T equals 5 gigayears or so, but then manages to maintain that star-forming gas by and large. And then finally, Romeo just continually accretes gas all the way down to about 10 gigayears before it finally starts to burn through that gas faster than it accretes it. So the short answer is every galaxy has a story to tell. So let's look at a couple of those stories. First, Batman. So Batman has this very interesting evolutionary history where it undergoes a double merger right here at about redshift 2 that funnels an enormous amount of gas into the center of the galaxy that forms this gigantic bulge that doesn't really do anything else for the rest of its evolution until you get this little bit of gas accreted at late times that forms your counter-rotating stellar disk. Then we have Remus. If you remember, Remus has this clear disk plus bulge. Remus similarly undergoes basically a head-on merger at redshift about 1.2, right there. That forms a bulge, but enough gas gets flung out, and then it manages to continue to accrete gas out of the hot halo to form a nice thin stellar disk in addition to that bulge at late times. Now finally we have Romeo. Romeo has basically no major mergers, or especially no head-on major mergers past about redshift 4. It just continues to smoothly accrete gas and build this larger and larger stellar disk all the way down to redshift 0. I'll just let this play for a second so you can see what it looks like at late times. I should put music in these movies. Okay, so just to summarize, here are the growth histories for our full sample. Again, I don't want to spend too much time on this, but what I want to emphasize is that these sharp early spikes in the amount of star-forming gas in the galaxy become far less pronounced and eventually disappear as the galaxies become more and more disk-dominated. So you go from systems like Batman and M12Q and M12B that have something happen early on that brings a lot of star-forming gas in, to systems like Romeo and Juliet that just slowly accrete gas all the way down to late times. So to quantify that, we went ahead and looked at some correlations. First, here I'm plotting disk fraction versus the amount of gas in the galaxy at redshift 0. I'm coloring by the radial extent of the galaxy. So you can see this is a pretty good correlation to my eye. Similarly, we can plot the average amount of gas in the galaxy since redshift 1. So this is basically the amount of gas available to form stars after the disk has settled down. This also correlates quite nicely. We can look at the average amount of cold gas in the halo, which is basically gas that is either in the galaxy or will accrete onto the galaxy, again, since redshift 1. And finally, we can look at, for example, the scale factor when the amount of cold gas in the halo is maximized. Here I'm just defining cold as less than 10 to the 5, somewhat arbitrary. But so you can see that this also scales quite nicely with both the disk fraction and our star. Okay, so I have about 2 minutes left. So in the remainder of my time, I want to talk about the morphology of the gas. You might not think that's enough time, but it turns out that the morphology of the gas in the Milky Way mass fire simulations is not incredibly interesting. Every single one of them, except for M12Q, which has effectively no gas, forms a thin rotation-supported gas disk by redshift 0. Now, this is actually, I think this makes perfect sense because at these masses, these halo masses, pressure cannot win against gravity. So any gas that is not rotation-supported is just going to collapse to the center of the halo and form stars on a free-fall time. So you must, by definition, basically have rotating gas disks, or the gas doesn't survive. M12Q, by the way, is in the middle of basically a blowout. So just to show you visualizations of our gas disks, these are, again, face-on, edge-on, you can see that, yes, all of our disks are very thin. except for a few cases down at the bottom where they have stuff accreting onto them. But the size varies dramatically, right? We go from little tiny things like M12C to these whopping huge disks like Romeo. So very quickly, the size of that turns out to depend very tightly just on the amount of gas in the galaxy. So M gas scales with R gas scales with M gas, I'm sorry. I've also colored this by the stellar radius, somewhat suggestively, because it turns out that the morphology of the gas also scales with the shape of the stellar potential. So for example, here I'm plotting R gas versus C over A. So here we have more disk-like stellar systems, and there we have more bulge-dominated stellar systems. That said, it doesn't necessarily depend on the things that drive the stellar morphology. So here's R gas versus the scale factor when the galaxy has its gas, right? And this to me looks like just a scatter plot. That makes sense if the gas morphology is just responding to the stars on relatively short time scales, right? Okay, so I'm about 20 seconds over, so I'll just leave my summary slide up, and thank you guys so much for having me, and thank you to the organizers.
So another of the things that you might compare to besides Romeo and White is so-called bathtub models, which predict that most galaxies will have a period during which the gas content is more or less constant, where, in other words, gas accretion is balanced by star formation and gas injection. Did you check that? And if so, what did you find?
I have not explicitly checked that. But going back to our growth histories, I don't think we really see evidence for that. So in a few of our galaxies, we have cases like in Batman up at the top left, we do have a long period of time at late times where the inflow and outflow is balanced. But by and large, the amount of gas in the galaxy is changing on, several gigayear timescales and on much shorter timescales. So you do have these large scale events that blow a lot of gas out, but also just on the timescale of a gigayear, right? Like Louise, Juliet, Romeo, these things are accreting gas much faster than they're turning it into stars for the majority of their lives.
Just a follow-up. Another thing that galaxies we know obey is the main sequence. Did you check that?
I've not looked at how we do on the star-forming main sequence yet.
It's a pretty tight correlation. These galaxies should be on the main sequence for most of their lifetime.
Yep, I should look at that. That's a good point. Thank you.
So when you plot the size versus scale property, why didn't you throw out all the high redshift points?
Why didn't I throw out all the high redshift points? Oh, I see what you're asking. That's a good point. I could put these galaxies on at higher redshift too. I was specifically interested in asking about morphology at redshift 0. The morphology, like we have a bunch of time steps, especially at late times, a bunch of snapshots, especially at late times. So over sort of 10, 20, 50 megayear time scales, the morphology is very, very constant. But you're right, I should look at redshift 1, redshift 0.5, and see what we get.
Any more questions? How are the you say that there are larger sizes of BRTs?
I'm sorry, can you say that again?
There are variety of BRTs, so you have a range of BRTs.
Yes.
And how are the values gained in the simulation? So are there different processes? Or
so by and large, based on what I've seen from looking at movies, pretty much, and I'm happy to show you all of the movie for every galaxy. Yeah, it's pretty much always that you have a merger at high redshift, which tends to come in with a low impact parameter and builds a bulge. Yep.
So, what sensitivity that's the disk fraction to this value? Use 0.6, 0.7.
I'll show you the plot later. It's not that sensitive. I mean, you're going to get different disk fractions, obviously, but the ordering of the galaxies is going to be largely preserved.
So I think we have to move on to the next speaker. It's going to be Tim, and he's going to talk about